We're going to prove that our product automaton construction is correct, in that it satisfies the desired property. So we have an LTS M with a state S0, and the automaton aut psi associated to an LTL formula psi. And we define the product automaton M as 0 times aut psi. The correctness theorem relates the words accepted by the product automaton with, on the one hand, the atom set traces of paths through the LTS M that start in S0, and on the other hand, the words accepted by the automaton aut psi. More precisely, let A0, A1, and so on be any infinite sequence of atom sets. Note that, on the one hand, this sequence is an infinite word over the alphabet sigma, which is the alphabet of both aut psi and the product automaton. On the other hand, this sequence is a possible atom set trace of paths in the LTS M. The theorem says that A0 and 1 and so on is accepted by the product automaton if and only if it is in the atom set trace of some path in M starting in S0 and is accepted by aut psi. This theorem follows routinely from the definition of product automaton. Let's see how. We have the following chain of equivalences. The product automaton accepts this sequence, A0 and 1, A1, and so on, just in case there exists in this automaton an accepting run for it. The states of the product automaton are pairs of states S in M and states K in aut psi, so a run is of the form S0, K0, S1, K1, and so on. Now, applying the definition of an accepting run and the definition of the states, the initial states, and the transition in the product automaton, we see that the previous statement is equivalent to the existence of an infinite sequence of states S0, S1, and so on in M, and an infinite sequence of states K0, K1, and so on in aut psi, such that the states Si transit between each other in M. The states Ki transits between each other through the AIs in aut psi. K0 is initial in aut psi. Each AI is in the labeling of Si in M. And also, the acceptance condition holds. In that infinitely many pairs, Si, Ki, are in every accepting set G of the product automaton. Next, we apply the definition of the product accepting sets, which essentially says that the product inherits the accepting sets from the automaton aut psi. So we replace the reference to these accepting sets G in the product automaton with a reference to the accepting sets F in the automaton aut psi. Now we apply the definitions of runs, of accepting runs, and of the notion of atom set traces, which give us a reformulation of the previous condition in terms of the existence of a path pi in M and of an accepting run in aut psi, such that A0 and 1, A1, and so on is the atom set trace of pi and is also the word accepted by the given run in aut psi. I use color coding to show how the various pieces are being reformulated, just a routine application of the definitions. And we further reformulate the last statement slightly, and then apply the definition of an accepted word to obtain equivalence with the desired statement, that there exists some path in M, starting in S0, whose atom set trace is our sequence, and auth psi accepts our sequence. And the proof is done. Okay, so we proved the correctness theorem for step 2. An important immediate corollary of this is that the language accepted by the product automaton is empty if and only if there exists no path in the LTS M such that its atom set trace is accepted by the automaton auth psi. Please pause for a few seconds to see why this is an immediate consequence of the correctness theorem for step 2. Now, putting together the correctness theorem for steps 1 and 2, we obtain an overall correctness theorem concerning the encoding of the LTL satisfaction relation in terms of automata. To achieve this, we use the product between the LTS and the negation of a formula. The overall correctness theorem says that, given an LTS M, a state S0, and a formula phi, we have that M in S0 satisfies phi, if and only if the language accepted by the product between M S0 and out of not phi is empty. The proof of the theorem is very easy once we have the correctness theorem for steps 1 and 2. It goes again by a chain of equivalences. The emptiness of the language accepted by the product automaton is equivalent by the corollary of the correctness theorem for step 2 with the non-existence of a path in M starting in S0 such that the automaton of the negation of phi accepts its atom set trace. Next, applying the correctness theorem for step 1, we see that this is further equivalent to the non-existence of a path from S0 that satisfies non-phi, not phi. Which means that all paths from S0 do not satisfy not phi. Meaning that they satisfy phi. But this is just the definition of M in S0 satisfying phi. This concludes the proof of the overall correctness theorem. Note again that this theorem reduces the LTL satisfaction problem, also known as the LTL model checking problem, to the problem of language emptiness for the generalized non-deterministic Buki automata, GNBAs. In step 3, we will show that this last problem is decidable.